Thank you, and thank you for the opportunity to speak today. And I'm going to try and give two examples of how advanced analytics can be used to inform both regulatory work as well as operations and the design and optimization of complex systems in two highly regulated industries. One is the food industry. This is basically work we've been doing for over 10 years, starting about 10 years ago with the work with the FDA here in the US, but then we currently have at MIT, at Sloan, work in China, India, Indonesia, and other countries. And then another very highly regulated industry, which is the pharmaceutical industry. This is, again, work we've been doing for now almost 6 years. And hopefully the two examples will illustrate the importance of being able to use data and advanced analytics to really improve both regulatory decisions, but more generally how these very complex systems operate. And I'm going to start with food and just a little bit motivate the importance of thinking about food and agriculture systems. It's fair to say that if you think about most of the global societal problems in the world, they connect with food and agriculture and water in a very direct manner. Starting with food security and hunger. Unfortunately, we still have hundreds of millions of people in the world living in hunger. But if you just think that this is just a problem of developing countries, if you expand the food security to nutritional security, then I can tell you that tens of millions of people in the US currently don't have access to fresh vegetables and fruits, and they live in what is called food deserts. So this is just by no means just a problem of developing countries. Food safety and food adulteration, food contamination and water contamination is one of the major reasons for illness and deaths in the world. You see the numbers here. Many of those cases are actually young children. And this is, again, not just a problem of developing countries. We have people dying from food contamination every year in the US, and I'm not even talking about the economic toll of that. Food and agriculture systems and water systems interact with the environment in two ways, in two bidirectional ways. The environment makes a major impact on agriculture systems. And at the same time, as you can see from the numbers here, agriculture systems are making a tremendous impact on the environment. Over 25% of the gas emission is actually sourced from agriculture systems. There are other issues like it's a major source of antibiotic resistance bacteria. And finally, and it's very relevant to the last 3 years, but more generally in the last several decades, agriculture systems were the source of multiple outbreaks of major pandemics of what is called zoonotic diseases or zoonotic viruses. These are viruses that emerge from animals and jump to humans and can cause major problems. I'm not going to talk about all of these issues today, but hopefully that kind of motivated the issue. So I'm going to give the first example I'm going to talk about is a project that is we are working on in China for over 6 years now. One of the things that I'm most proud of is this is really a multi-collaboration projects. We have been collaborating multiple faculty here at MIT from 3 schools, the School of Management, the School of Engineering, and the School of Sciences, with 5 academic and private organizations in China that never worked together before until they started to work with MIT. And this is with the funding from the Walmart Foundation. And the first example is going to talk about data. Data is a major issue in these industries. Data is very fragmented. And I think the next example is going to illustrate that. So the China FDA, which is perhaps the main organization in China that regulate the food system, one of 2, but the main one, is actually mandated by law to put all the test records of food products in China in the public domain, surprisingly. But the regulatory environment in China is highly fragmented. So you end up having on the left-hand side, what you see here is the central state-level website that has a little bit more structured data. But then on the right-hand side, you have hundreds of sites for each province and each prefecture city in which the data is being posted in completely unstructured form, completely ad hoc forms. And the data basically resides on 400 sites, give and take. And it's not very usable. What we were able to do over the last several years with a team of basically 1 or 2 people using machine learning algorithms and text analytics algorithms, we are able basically to scrape the data from most of these websites, and we are able to structure them into a unified scheme. Essentially, at this moment, we have more than 10 million records dealing with tens of thousands of unique formats, all with a team of 1 person leveraging at scale algorithms. And let me show you a few examples of what the algorithms are doing. So what you see on the left-hand side, this is the raw data. This is just describing a test in a given city in a supermarket. What we are able to do here on the right-hand side is to detect automatically what is the city, but also what is the supply chain location. In this case, it's a retail supermarket in which the test was conducted. The second example, this is on the left-hand side, you see a specific product. We are able to automatically characterize and identify the product category. So then you actually have the ability to fit this into product categories. And finally, the last example is a failed test. We are able to detect that the test failed, but also what were the other trends that were detected in the test. Again, all of this is being done in an essentially automated manner using different range of algorithms. So now, having this data, what kind of analysis we are able to do? So what you see here is for some reason the animation is dead, but so what you see here is the schematic, very complex supply chain of one of the highest risk product categories, which is freshwater grown seafood. In Chinese culture, seafood is being consumed fresh and alive, actually. So as you can see from the left-hand side, many farms. Unlike the US, we are talking about millions of farms, mostly family farms, very small, that produce the shrimp or the seafood. They then sell this through a network of brokers, either to manufacturers or to large wholesale markets in the middle that basically distribute this then to secondary wet markets and to retailers and restaurants. Now, the Chinese government is primarily testing in retailer stores. We can talk about in a different time why, but that's the fact. But what we wanted to see is not where the tests are being conducted and perhaps failing. We wanted to see what was the source of the risk that was introduced into the supply chain. So for example, if the test of a product in a retailer store failed because of detection of illegal antibiotics residues, it probably means that the farming part of the supply chain introduced that risk. On the other hand, if this was a preservative that is not allowed, that's more likely to be the source by the manufacturer, right? So what you can see here, based on the data that we have, we can automatically take all the failed tests in retailer stores and understand what is the source of the risk, where the source in the supply chain was introduced. And what you can see here that about 40% of the risk was introduced in the farming stage. Over 45% was introduced at the manufacturing level, 8% from the environment, and the rest is from the transportation part of the supply chain. And this is already a very major insight because it tells you that the current policy of the government does not test at the source of the risk. It tests at the downstream parts of the supply chain, but not where the risk is being introduced. Now, to operationalize this insight, we were able, what you see here is an interactive tool that we've created that basically highlights what we call high-risk manufacturers. These are manufacturers that their products failed at the retailer store because of another trend that is very likely to be introduced by their own practices. And what we were able to show that if you actually go and test these manufacturers on site, you are likely to increase the problem detection by about 4-fold times compared to just randomly sampling manufacturers. So you can actually see that we can take these insights and translate them to very operationalized recommendations, again, using data and predictive algorithms to essentially guide where tests should be conducted next. Another thing that is very unique about the supply chain in China, other than that it's very complex, is the existence of these large wholesale markets. If you think about the supply chain that we see here, there are millions of farms, there are millions of restaurants on the right-hand side, but surprisingly, there are about 5,000 large wholesale markets in China, and in China's scale, that's a very low number, that essentially consolidate about 80% of the supply of many important product categories, including seafood, but also vegetables and fruits. And this is really an attractive opportunity because in a relatively small number of locations, you can actually touch and inspect and try to control for the quality of a lot of the supply in the supply chain. But actually, we are able now to see how the tests are being allocated. This is the blue boxes here. You can see, as I mentioned before, that almost all the tests, more than 50% of the tests, are allocated to retailer stores, and a relatively small fraction of them are being allocated to wholesale markets and wet markets. And that's contradictory to the fact that the failure rates in these places, in these locations, and you can see the failure rates, again, based on the data that we have, we can calculate them. These are the orange boxes. The failure rates in these wholesale markets are actually higher. So that kind of led us to focus greatly on wholesale markets, and what we wanted to do is to develop a risk metric of each one of the wholesale markets in China and the wet markets in China. That was actually a challenge. And the challenge came from the fact that in order to do that, you need to be able, in the records that we have, to associate them with individual markets. And we don't have a list of all the names of all the markets in China. This is a very big list. Beyond the 5,000 large wholesale markets, there are many, many smaller wet markets. So it's actually a pretty big challenge. So what we needed to do in order to do that, we had to develop an algorithm, a clustering algorithm, that in an unsupervised way will be able to allocate and aggregate all the records in our database set that belong to are associated with a single individual market. Existing algorithms did not work because the Chinese language has very different structure than the English language. So most existing algorithms do not work. In order to do that, we needed to really use the way the Chinese language is structured, and specifically how the names of the markets are being posed. And we developed a state-of-the-art algorithm that really achieved, even under very strict metrics, over 90% accuracy. And again, this translated to another tool that you can see here that essentially highlight all the high-risk markets in China. And what is interesting that we were also able to show that the food safety risk that the market has is actually highly correlated with other risks to human health. For example, being a source of outbreaks of zoonotic diseases. In fact, most of the outbreaks of zoonotic diseases in China came from China over the last several decades, and they came specifically or were associated with wholesale markets in China. So this seems to actually have a broader impact than just looking on food safety risks. Okay. So hopefully I gave you some examples of what you can do in the food space. Let me switch to talk about an example from the pharmaceutical industry. And here, the issue here is that when you think about the manufacturing environment of biologic drugs, it's a highly regulated environment. In fact, it's being operated under very strict control limits. And every time you deviate from these control limits, you have to investigate and file a regulatory report and document what was the deviation and how you fixed it. The problem is that most of these deviations are actually being saved as free text. And that makes it very, very hard to understand long-term trends or even learn from one example to the other. So if 2 years later you had a similar problem and your investigator changed, nobody is going to remember that, and they will have to, at best, do some search on free text to try and understand if they ever saw that problem. So the goal here was, can we somehow augment the current documentation of these deviation reports and structure them in a more meaningful way to allow more structural analytics and understanding of trends. And a very natural way to try and classify these deviation reports is to think about what is the specific process step. And here you see the different steps of one of the process steps, the bioreactor, which is a major part of the manufacturing of biologic drugs. So essentially, can you can you take the deviations that you have, the corpus of deviations that you have, and try to classify them into the specific process step or the specific piece of equipment to which they were related, and then, of course, do the same to the solution or to the intervention that you implemented on the line. Now, as you can imagine, this is a corpus of documents that is unclassified, multiple years of deviation results. So one approach could be put some experts to classify and label hundreds of reports, and then apply some supervised learning algorithms to do that. That's not very practical. So what we actually did is to leverage what we call side information. On each one of these process steps in this environment, there is a lot of text that describe, and this is called SOPs, Standard Operating Procedures documents, that describe how these process steps should actually operate. And what we did we used that, we call those category descriptions. We took for each one of these process steps the documents that describe the process step, and we wanted to see, can we leverage them to classify the deviation reports that we have. Now, a more formal, generalized way to kind of describe the problem is, on the left-hand side, you have multiple documents that you want to classify into specific categories, and on the right-hand side, these are outside information that you're able to gather that describe each one of the categories. It's a text that describes these categories, and our assumption is that while the deviation on the left-hand side were not created from the same distribution as the category description, they are similar enough that they could be useful. So the actual algorithm was, we were using initially the category description to classify each deviation report to the closest to it in terms of the category descriptions, and then applied iterative improvement by taking the initial labels that we had and retraining multiple times. And as you can see, this has been performing extremely well. In fact, we are almost matching what you could do with supervised learning, assuming that you labeled about 30 to 50% of the data. In fact, we were able to generalize this and apply this approach not only to the pharmaceutical data that we had, but actually also to other data sources, other data sets that are completely different. So that seems to be quite a general approach. And in fact, we are now thinking about how to explain, to create a theoretical model that explains what we see and why these algorithms work very well, which is essentially the core modeling aspects here is to really think about the differences between the distribution of words that created the original deviations and the distribution of words that created the category documents. And what we see from the real data, that the differences between the two are the following. So if you look on the left-hand side, one way to think about here is that there are two categories, and each one of them has the specific words that appear in higher frequency for those categories. These are the green bars that you see for each one of them. On the right-hand side, you see the reference information, the category description. As then you can see, some of the words that are specific for the deviations are not specific in the description. Some of them are actually misleading, so there are some corruption. And what we actually are able to show that you can, under some modeling assumptions, you can actually boil down the analysis of what are the probability that you're going to be wrong or right to some biased random walk. And we are actually able now to show that using side information, as long as it's reasonably well, is going to actually perform well. And in fact, the iterations that you're going to do to improve are going to improve your performance actually quite significantly. So as you can see, there is also some theory that emerging from this more applied work that we are very excited to do. So just to summarize, hopefully I gave you some examples of how you can use AI and data at scale to inform regulatory and operational decisions in two highly regulated industries that have major impact on human health. I want to emphasize that one of the major challenges is how you actually structure the data, and in fact you can use machine learning to structure the data and create usable data that you can then use. And the second thing is that you really need to think about this in the context of other aspects, like for example, if I think about the wholesale markets, how do you improve technologies that test products and so forth and so forth. So this is not just merely a data issue. There are many other complementary actions that you need to consider. So thank you very much for your attention.
is ramping up. If there is one question. If not, thank you for your, oh, yes, please.
Hello, my name is Baturul. Thank you for your talk. My mother tongue is Mongolian. As a result, I'm very curious, what were your findings from working in a different language other than English? Any lessons you learned that you can teach the other speakers to make use of these technologies in different languages? Thank you.
Yeah, I'm not sure that my Chinese now is something to be proud of, but I think that this has many technical issues that are you have to think about them, because the structure of Chinese, for example, is completely different. So that's actually interesting, but I think that there are motivations to actually understand AI for Chinese, other than just translating into English and apply what you want. The algorithms that exist in English. Sometimes it actually works well, by the way, but not all the time. And the second thing is, which is not related to AI, when you work in an environment like this, being able to have at least people on the team, some people on the team that speaks the local language is actually absolutely critical to understanding what's going on. And I've been spending many hours in the room with maybe being the only person not knowing Chinese and having to rely on translation, which is kind of an interesting experience. So yeah, but I think if we want to solve global problems, we'll have to deal with different geographies and different languages, and we cannot just stay with English. So I recommend my kids to learn Chinese now. So.